what we're going to look at today is something called implicit differentiation. So we would say that an explicit equation is an equation where you can get y all by itself written as one variable in terms of the other variable. So I can get y equals 3x squared minus 2 as an explicit equation because I have one equation in terms of x. However, sometimes you have an implicit equation where you have a relationship between the two variables. In this case, it's not even a function. If I have x squared plus y squared equals 16, does anybody know what shape that makes? It makes a circle. It makes a circle with a center at 0, 0 and a radius of 4. So we can't write this all as one equation, because what happens if you try to solve for y? If I try to get y by itself, well, I can subtract x squared on both sides. And if I want to get y by itself, well, I would have to take the square root of both sides. And when you take the square root of both sides, one time you could take it with positive, but the other time it might have been negative. So we end up with two different equations, and there's a relationship, but it's not a function. A circle is not a function. It doesn't pass the vertical line test. Question is, can we find derivatives of relationships? Can we find, if I have this circle at 0, 0, 1, 2, 3, 4, 1, 2, 3, 4, and a radius of 4, this is what this, wow, the best looking circle you've ever seen. Have you ever gone online to like circle drawing competitions? They have people that go up to the board and they sort of have trained their arm to be like a radius, and they draw a perfect circle on the board every single time. And it's really quite, I'll see if I can find a YouTube video for you. Okay? We'll do this question first. We'll introduce this idea, and then we'll look up circle drawing videos after. But to start off with, we've got these two equations. The question is, if I wanted to pick a point on here, say at x equals 3, and find the slope of that tangent, that would be one slope of the tangent. There would be another one down there when x is equal to 3, because this graph has 2 points. So how do we go about doing it? What we do is we find the derivative of our entire equation on both sides. So the process and what we're going to look at with explicit differentiation is if we had something like x squared plus y squared equals 16, we're going to take the derivative with, in this case, with respect to x of the whole thing. What's the derivative of x squared? That's easy. That's 2x. What's the derivative of 16? That's easy. It's 0. But what's the derivative with respect to x of y squared? Well, this is where things get a little bit tricky. So the concept is, and this example that I did is an example where if you wanted to, you could get y by itself and there would be two different equations. So we were able to get y by itself, and there's two different equations. However, some equations you will not be able to get y by itself, and all you can say is that there is some function y that could be written in terms of x. I just don't know what it is. Okay? So when I'm taking the derivative of y squared, it would be a chain rule. Because this would be my function, right? I have y equals something, and it's getting squared. And there might be an x in here. So this is really theoretical right now. So We've got some equation that's squared, and we've got, that's what y equals. How would I do the derivative of this whole thing? Well, it would be a chain rule. Can you see that my derivative, dy dx, would be the 2 would come in front, keep the inside the same, which might have an x, subtract 1 from the exponent, multiplied by the derivative of the inside. What's the derivative of the inside? The derivative of the inside. Okay? So now let's say, same process here. I have a squared. My chain rule would say, do the outside function first, keep the inside the same, subtract 1 from the exponent, multiplied by, what's the derivative? And I guess I don't need to write a little 1 there. Actually almost looks like y prime. So, and then what's the derivative of the inside? The derivative. This is the big idea of implicit differentiation. That if you have a y, you imagine y could be written in terms of x, and then the derivative of that would be the derivative. And what this allows me to do at this point is it allows me to rearrange this equation and say 2y dy dx is equal to negative 2x, and divide both sides by 2y, and my derivative is equal to negative x over y. The 2's would simplify away. And so I have an expression for my derivative that's in terms of x and in terms of y. Something that we can see from our circle. Can you see that at the very top of your circle, you would have the point 0, 4. Your x value would be 0. Your y value would be 4. If I drew my tangent here, it's pretty obvious that that would be a horizontal line, and that my slope would be 0. If I go to the formula that I just created, dy dx, my slope should be negative x over y, which would be 0 over 4. I would get 0 at that point. If I chose this point originally, which was at 3, if I plug 3 in, okay, for x, 16 minus 9 would be 7. Square root both sides. Can you see that this one would be 3 comma positive square root of 7? And this point would be 3 comma negative square root of 7. Those would be the two possibilities. I can now say that the slope of this line from my derivative is negative x over y. I can say the slope of this line is negative 3 over root 7. And the slope of this line is negative 3 over negative root 7. Which is kind of fascinating that we're able to do that so easily. So the idea with explicit differentiation, to make it really simple, okay? So right now at the beginning, I'm really trying to explain this so that you can understand it. And at this point, I don't expect any of you to understand it yet, because it's a complicated idea. Now I'm going to teach you how to do it if you have no idea what's going on, so you get it right every single time if you like. Sometimes that's a good thing. What do? We do the derivative of the whole thing just like normal. X squared is 2x. The derivative of y squared would be 2y. But every time that you have a y and you do the derivative, right after you write dy dx. Because of the chain rule, but we'll try to explain that again later. Equals 0. Well, equals 0 because that's the derivative of the other side. Then rearrange your equation to get your dy dx by itself. This is a fascinating equation because I could have figured out dy dx separately for both of these. I'd like to do that right now to hopefully give you some deeper understanding of what's going on. If I wrote this one as 16 minus x squared to the half, can you see that you could find the derivative if you used the chain rule? Y prime would be 1/2 bracket 16 minus x squared to the negative 1/2. Derivative of the inside would be negative 2x. If I simplified this, can you see that the 2's would simplify? And I would be left with a negative x in my numerator and the square root of 16 minus x squared in my denominator. And what's fascinating about this, oh, this is dy dx, sorry. What's the bottom? The bottom was just my original function, negative x over y. Same as we found with implicit differentiation. Kind of interesting. And we could do the same thing with the negative out in front, and it works again. So the idea with implicit differentiation is that if it were possible to get y by itself, you could do the derivative, but then noticing a pattern in the end that y shows up again later. So when we go to example 2 here, okay, well, we just did this one. Sorry. When we go to this example, this one, as much as you would like to try, is next to impossible to get the y by itself. Because there's a y here, and there's a y to the 7 over here. So to make things simple for implicit differentiation, we take the derivative of the whole thing. So and we imagine that you could somehow get y by itself as some function with an x in it. And there exists a derivative, dy dx, or y prime. I like to use Leibniz notation here because the dy dx really stands out. But this question says find y prime, so we'll use y prime notation. So what do? We find the derivative of each thing separately. Okay? I'm just going to make some notes about each thing. This is going to be easy. I'm going to put a little smiley face, because that's easy to do the derivative. This is going to be a product rule because you have an x cubed times by a y, and y is some big thing with x that we don't know what it looks like. This is going to be easy, derivative of 15. And this is going to be relatively easy. Whew. How do you do relatively easy? You kind of smiling? Well, yeah. Okay. I don't know. Those aren't official math symbols. Just made those up. So I'm doing the derivative of everything. 3x to the 4, easy. 12x cubed. Things are going well. Minus. What's the derivative of x cubed y? It's a product rule. Product rule says keep one the same times by the derivative of the second one. What's the derivative of y? The derivative of y. Does that make sense? The derivative of y would just be the derivative of y? Now, technically, if you just did the derivative regular, what's the derivative of just x? You would get 1. But every time that we have a y, we have to do the chain rule, and then afterwards, you'd have to multiply by y prime. I think in this situation, it's just easy to say the derivative of y is the derivative of y, because that's what we're looking for. Product rule continues, then you add, now you keep the second one the same, which is just y, times by the derivative of the first, 3x squared. Why did I put that all in brackets? Because of that nasty minus sign in front. Because you're subtracting all of this, so when you do the derivative of all of that, it all gets subtracted. Sometimes what I like to do with a minus sign out in front in implicit differentiation is I might have started this equation by rewriting this as 15 plus x cubed y minus y squared. I might even move the y squared over to the other side, so I'm only dealing with positive numbers, because those negatives can cause a little bit of a problem. So I've done the whole left side equals the derivative of 15 is 0. The derivative of y to the 7 would be minus 7y to the 6. And because it's a y, we'd have y prime after. Okay? And now what we want to do is we want to solve for, right? This question said, find y prime. Well, I have y prime in two different places here. I have a y prime there, and I have a y prime there. And I want to get y prime by itself. So what I'm going to do is I'm going to move every term with a y prime to one side of the equation, and all my terms without a y prime to the other side. So I'm going to move this 7y to the 6 times by y prime to the left. I would still keep the minus x cubed times y prime on the right. And everything else, so that 12x cubed gets moved to the left. I would have a negative y at 3x squared. So I'm going to add that negative to the other side. So it's going to be plus 3. I'm going to write it as 3x squared y. And I have two terms still with the y prime in it. If I want to get the y prime by itself, I could factor that pretty yellow number out. At which point, if I wanted to get y prime by itself, oh, sorry, I haven't divided. I was thinking of the next example I was going to make up. There we go. And so we get y prime all by itself, and it's in terms of x and y. So we had a product rule built in. Everything else was straightforward. Notice whenever you're doing the derivative with a y, that's when y prime or dy dx is going to show up. Again, can you see with the notation how you might think your y prime looks like a y to the 1 depending on how slanty you make it? So for that reason, I like using dy dx whenever I'm dealing with implicit differentiation. This is a nicer example because there's no negatives. That makes it nicer. because that negative could cause us a problem. I think I would recommend moving negatives to the other side of the equation just so that you have positive numbers. We have a cube root, so before we start, I'm looking, no negatives. I'm going to change my cube root to y to the 1/3. Okay, I'm going to make some notes. X squared, that's easy. Y to the 1/3, kind of easy. It's going to have that y prime in it. This is going to be a product rule. We'd have a 3x to the 4 multiplied by a y cubed. And this one's going to be super easy because that derivative is going to be straightforward. So I'm going to take the derivative with respect to x of this whole equation. Easy part. X squared derivative is 2x. Y to the 1/3. Just 1/3 y, subtract 1 from the exponent. And any time you do a derivative with y, you multiply by dy dx after. Equals. Here we have a product rule, so I'm going to put it in brackets. Keep the first one the same, times by the derivative of the second one. The derivative of y cubed will be 3y squared times dy dx. Plus, keep the second one the same, which was y cubed, multiplied by the derivative of the first one, which will be 12x cubed. And then the derivative of 8, you wouldn't have to write plus 0, but just so that we looks like we didn't forget about it, I'm going to write plus 0 at the end. How many terms have the derivative in it? We have the derivative here and the derivative here. And that's what we want to solve for. So I'm going to move all of my terms with the derivative to one side of the equation and everything else to the other side of the equation. So I've got a 1/3 y to the negative 2/3 dy dx. I'm going to move this term over, minus 3x to the 4, 3y squared dy dx. And I'm left with a y cubed times 12x cubed, and I'm going to subtract the 2x on the other side. Now that you have dy dx all on the left side, there's two terms with dy dx. You can factor that out, leaving you with 1/3 y to the negative 2/3 minus, now here I have 3x to the 4 times 3y squared. We can simplify this a little bit. 3 times 3 is 9. As far as putting variables together, you tend to put them alphabetically, so you'd put your x first and then your y. Same thing here. I would write this as 12x cubed y cubed minus 2x. Forgot to close this bracket there. Now that you've factored out that dy dx, you can just divide both sides. So this would stay the same up top here. And we're dividing by 1/3 y to the negative 2/3 minus 9x to the 4 y squared. So we get an equation of the derivative. Okay? We get an equation of the derivative, and it's in terms of x and y. And this is helpful, especially in cases where we can't get y by itself easily. Okay, I am going to make up an example to show you how this is working. So you don't have to write this down. You can just watch. But we're going to do something like, something simple. Y squared equals x. Find dy dx. So if I was doing the derivative of this, I would do the derivative of both sides. This side, 2y dy dx. And on this side, it's just going to equal 1. So to get dy dx by itself, is 1 over 2y. Okay? Now let's say y is equal to, I'm not sure if this is going to work, but I want to play around with this. Let's just say y is equal to x cubed. Can you tell me what the derivative is? I'm trying to think if this is going to work nicely or not. The derivative is 3x squared. So now, how do I want to manipulate the other side. I'm not sure if this is completely good or not. No, what I wanted to show doesn't work with this. So, it was an attempt at a good idea that didn't work. Oh well. I wanted to show something similar to what we saw at the beginning when we could either do it as implicit differentiation or as regular differentiation, and they work out to be the same thing. But in our case, I started with two different equations, and that went wrong. If, however, okay, this is what I started with, right? I should go back to that. Let's go back. There we go. Let's go back to this and instead actually solve for y. This will work better. If I square root both sides, I would get plus or minus x, right? Yes, this would work better. So one of the equations is x to the 1/2. The other equation would be negative x to the 1/2. Could you find the derivative of x to the 1/2? Yes. dy dx is 1/2 x to the minus 1/2. What does that mean? What does that look like? That looks like 1 over 2 times the square root of x. The square root of x was the same as what I started with, which was y. And so this equation using the actual solving for y works out. It works out for this half. Question is, would it also do the same if I tried the other half? If I did on this half, what's dy dx? Well, I bring the 1/2 out in front, which would give me negative 1/2 x to the negative 1/2, which is negative 1 over 2 square root of x. Where I put my negative in a fraction, do you agree that negative 2/3 is equal to 2 over negative 3? It's a little controversial. They're the same, right? Does it matter where that negative is? So that means I could have had a positive 1 on the top and the negative on the bottom. The next controversial thing to think about, would you agree that negative 2 times 3 is the same as 2 times a negative 3? Yes. Does it matter where the negative is when you're multiplying? No, so I'm going to manipulate a little bit more and say this is equal to 1 over 2 times, I'm going to put the negative there. Why am I doing this? Because what did I start with originally? This one started with the square root of x. This one started with negative square root of x. And this side is also 1 over 2y. Now, in this example that I did, we were able to get y by itself, because you can square root both sides. And then you could find the derivative of both of them separately, and then you would have to know when I could use one and when I could use the other. But implicit differentiation says, don't worry about that. Just do the derivative and imagine that y is a function of x. So when I do the derivative of 2y squared, my 2 can come out in front, the inside stays the same, and then multiply by the derivative of the inside, which is the derivative I'm trying to find. So you can remember how to do it through the simplistic way of just whenever I have a y and I do the derivative after I write dy dx. And that will work for you. But what I've tried to do is give you some examples so you can understand what's happening and why it works.